streaming part. It's similar in the second stage. The join, you can do a full join, which does a batch job, and you can also do an incremental join. Whenever things change in the HBase table, you want the change gets reflected in the result table at real time, which this is very similar in the final phase, in the export phase. So traditionally, this is done using two completely different pipelines, which is not the best way because you may need to duplicate your code twice and maintain two pipelines. We want a uniform framework to be able to handle such batch processing and streaming processing uniformly. So you probably have heard, if you are in streaming background, you probably have heard streaming is your new database. This is the example where this is literally true. If you look at the HBase tables, it really converts your strings into a table. And at the same time, the replicate table, the RIC and the UIC tables, whenever they change, they also deliver strings to the next stage. This is the inputs to the next stage, and which allow it to do string processing and produce result to the result table. So this is where you see string is your database, string database duality in action, in reality. When we want to unify the streaming processing and batch processing, in this example, if you look at the second stage, especially if you look at the join stage, for people with database background, they will immediately recognize this something, and this is something very familiar in database community, which is materialized view. You can consider the result table as a materialized view of the input table, the IC and UIC tables. Basically, you write some query in a database, in a relational database system. You can write some query which does the join aggregation and say create a materialized view on this. Then the result of the query will be stored in some tables. But better than that, when you make changes to the input table of your query, the result gets updated immediately to make sure the result is consistent with the input table. This is exactly what we want in our case. So this gives us some hint on how we can unify the batch process and the streaming process. In terms of materialized view, the batch process is really index creation or index rebuild. And the streaming part is really the index maintenance, which automatically happens when your input table changes. So we decided to take this view and have a unified system. The way we want to describe the process is to have some high-level description of the transformations we wanted. For example, we can have some in materialized view in database community. We use a SQL to describe it. Here, we can also use something like SQL, but it doesn't have to be. Let's say we use something like SQL to describe the result table from the input tables. This approach, and when we do that, we want to make sure the same SQL works in the streaming mode. This is actually a very different, a unique approach from other streaming SQL. Traditionally, when you do streaming SQL, especially if you have a group by clause, they will require you to have a monotonic current so they can know when you can produce a result. Even for simple queries like word count, imagine your input table is a table which containing all the words, and your result table has two currents. The first current is a word, the second current is the count. In batch, it's a very simple query. You can do a group by and do a count and get the result. But in streaming, lots of streaming systems don't allow you to write it very intuitively because there is a question about when do I do the calculation. In a streaming scenario, the input table never finishes. So there is no good time for you to do the calculation if you want to get the correct result in one shot. So a lot of streaming SQL force you to add some time current or time window in streaming queries, which in my view is a bit awkward, but it's required because the model is to try to get the result in one shot. But in our case, due to the database and string duality, the result is not immutable. It allows you to update your result later. So in word count, you can, if you hello appears 3 times, you can emit count 1, then 2, then 3. You can update it later. So this freedom makes it possible for us to completely unify the batch SQL and the streaming SQL. And this is also an approach that realizes the database and the string duality to its full extent. So imagine in this case, when you do this join, you can do it in batch. IC table and UIC table, you do it batch. You will produce a correct result. You can also do it in a streaming fashion. Imagine all the tables are completely empty. Then you get all the changes to your input tables. Then the final result table will be exactly the same as if you did a batch. You can even do a mix. You can take an initial snapshot of the input tables, do a batch. Then at the same time, do whatever delta updates you have made to the input table and produce exactly the same result. This unique approach makes it possible to have the same description of your business logic in both batch mode and streaming mode, and gives you the freedom to choose which mode you run your query. So this is what we take. So we started looking for what's the best way to do this, and we discovered Flink. Flink is a unified computer engine. It supports both streaming and the batch process. It's unique in its approach because the underlying engine is always streaming. Even for batches, it's the underlying runtime is done in a streaming fashion. And in the streaming support of Flink, it supports stateful computation and exactly once semantics. This is the stateful the state support in Flink gives you the freedom and the power to express a lot of complex operations that you may need. And exactly once semantics makes sure you can always get the exactly correct answer in your system. This is the Flink ecosystem of Flink stack. You can see at the bottom there is a unified runtime which supports both the streaming processing and the batch processing. On top of it, there is the dataset API, which allows you to do batch jobs, and there is a data stream API, which allows you to do streaming job in a pretty high-level description. Recently, the Flink community has announced the support of Apache Beam API, which will unify both streaming, the dataset, which will unify both streaming and batch processing in one single API. And Flink is probably the best open source project that supports it. On top of this operator layer API, there is also SQL level API, which is called table API in Flink. It supports both Scala-style SQL and real text SQL. In addition to this, there are some other libraries like complex event processing and machine learning libraries in the Flink ecosystem, and it keeps growing. So this is great. We were pretty excited about the promise of Flink architecture and decided to give it a try. So we take a much closer look. And we discovered a few issues that might be that might be problems at production. So we decided to improve that. And that's how we started the Blink project. Blink, it's a project we started at Alibaba to make sure Flink is really up to the production quality at a very large scale. And the name Blink tells you the latency of its process. It will finish your string in a blink. The improvements to Flink comes in two categories. The first set of improvements is at the SQL layer, at the API layer. Currently, Flink have a reasonable support for SQL, for batch SQL. But the support for streaming SQL is still primitive. It only has, basically, it only has a select and where statement in streaming. We want to make sure the support for at the SQL layer in streaming is functionally complete to meet our functional requirements. In addition to this SQL layer, we also made a comprehensive improvement to its underlying runtime to make it more scalable, more robust, and easier to manage in production. With this project, we were able to put Blink in production in Alibaba Search. For the two use cases you see, they are already in production and serving the traffic. They are running on a cluster of 1,000 nodes, and each one have thousands of calls. I'm going to talk a little bit more about the improvements we made to the table API. The philosophy we take is we want a unified SQL layer for batch and streaming. As I explained earlier, I'm a deep believer in string and database duality. We want to make sure you can use the same SQL when you do batch job or streaming job. You don't need to write your business logic twice. More concretely, we made a set of improvements to its functionality. The first category improvements, the first set of improvements are user-defined function, which allows you to write your business logic. And we also introduced user-defined aggregates in case you have some aggregation logic that's not built in. For user-defined table-valued function, this is introduced to allow you to join a string with some table, for example, a HBase table. In addition to this, we introduced string-to-string join. This is actually not so easy, and it's a full demonstration of the power of Flink runtime. Flink, as I just pointed out earlier, Flink is a it's a stateful streaming solution, which means it handles state in its runtime, so users don't need to worry about it. It makes it very easy to express complex logic like string-to-string join. When you join an impression string with a click string, there are a bunch of problems. First, the click may happen many minutes later than the impression itself. And sometimes the event order can be wrong. You may get the click first before you get the impression. To deal with such issues, you actually need to save some data in your state, so you can look it up later. Because Flink handles the state and for you, this is pretty simple to do in Blink. The states, even in the case of failure, the states will be failed over correctly and produce the correct result. Next, we also introduced a set of important built-in aggregations in our system. The more difficult one is probably distinct count, which is non-trivial to do, because that also requires you to keep a lot of states. In terms of windowing, we added the support for time window and the count window for now. In the future, we may extend it to add more comprehensive support. And finally, the interesting thing is about retraction. So as in the example earlier, in our streaming SQL, we allow you to update your result. So for in the word count example, the count for a specific word may be updated later when you when the same word appear in the input again. This is the updating itself is good enough in this case. But imagine after you do a word count query, you want to do another query which just count all the words in the system. You can do it in batch mode. It's very simple. You can get the word count result and sum all the counts together. You will get the number of words in your whole system. But in streaming, this is not sufficient because in the case of hello appear 3 times in a string, you will see hello 1, hello 2, hello 3. If you simply add them together, you will get 1 plus 2 plus 3, which is 6. And the correct answer should be 3. So how do we deal with it? In this case, we need to make sure when we update the result, we let the downward string know. So when we change the result from 1 to 2, we will also output another record retraction of 1. When we update the result from 2 to 3, we will output a retraction record for 2. So in this case, you will get the final correct result, 3. OK, now let me turn it over to my colleague Feng. He's going to give more detailed explanation of what we did to the runtime.
Oh, good afternoon. All right. I'm Feng from Alibaba, with the same team with Xiaowei. OK, next I will introduce the runtime improvements we did for Flink. At first, I will introduce the Flink new runtime architecture, native run on yarn. And secondly, I will introduce the optimizations we did for Flink state, checkpoint, and failover. Moreover, we also do some works to make Flink stable enough to be run for production. OK. Before introduction of the Flink runtime architecture, I will show the Flink class modes first. Flink has 2 class modes. One is standalone cluster. Another is cluster run on yarn. The Flink standalone cluster consists of 1 job manager node and several task manager nodes. Obviously, the standalone cluster mode cannot share resources with other kinds of applications, such as MapReduce, Sparks, etc. So Flink also supported cluster running on yarn. But after the Flink cluster launched by yarn, it cannot reallocate any resources anymore according to its workload. So the resource management of Flink is not dynamic. Different Flink jobs always maybe run in the same Flink task manager container. So they are not really isolated on the yarn cluster. OK. To solve this problem, Flink implements a new runtime architecture, native run on yarn. The first, the Flink client will submit a job to the yarn cluster. Then the yarn resource manager will launch an application master first. We call it Flink job master. Then the job master will allocate resources from yarn resource manager first, and then use this resource to launch several task executors through the yarn node managers. And then assign their job task to the task executors. After all the tasks finish, or the job finish, the job master will release all the resources to yarn and quit itself. So the resourcement of the Blink architecture is dynamic. And of course, different Blink jobs run in different Yarn containers. They are isolated naturally on Yarn. Okay. Next, I will show more detailed information about the Blink job architecture. The Blink job is composed of two components. One is his job master, and another is called task executor. The job master is responsible for the task schedule and the checkpoint coordination. And the task executor is responsible for the task execution and the state management. Periodically, the job master will trigger a checkpoint to the stream. Then all the tasks running in the task executor will do the RocksDB local snapshot first, and then copy the snapshot files to HDFS, where it can be recovered from in the next start. So because the checkpoint and the state management is very critical to the streaming. So next, I will show the optimization we do for Flink checkpoint and state. Let's see the Flink checkpoint workflow first. The job master will trigger checkpoint in cycle, and the tasks running the task. All the tasks will receive a special checkpoint barrier, which is a special message sequentially. Then the task will first do a local snapshot for the RocksDB first, and then this is synchronized, and then do backup the files, the snapshot files to HDFS asynchronously. In the first stage, Flink uses deep copy mode, which may take several seconds, maybe more, according to the size of state. This may also pause the stream. But in Blink, we use hard link snapshot mode, which may only take milliseconds. And in the second stage, Flink uses complete backup mode, which will always copy all the snapshot files to HDFS in every checkpoint. This will cause many redundant I/O. In Blink, we use incremental backup mode, which only back up the different files to HDFS between the last successful checkpoint to now. So Blink checkpoint and the state management is more efficiency, and barely pause the stream. Okay, I will show another. There is another critical issue about Flink is Flink cannot rescale its job graph after the first start. In other words, user cannot change the operator paradigm after start a job. So in order to solve this problem, Blink add a new bucket layer between the key space and the operators. First, Blink map the key spaces to different buckets, then assign different buckets to different operators, partitions. This decouples and partitions the state storage by the buckets. So this decouples the storage state partition with the operate paradigm. So by this method, the operator paradigm can be changed dynamically within the bucket size. So Blink can rescale the job graph in our production. Okay. As we know, the stability is a major concern for every systems. So in order to bring Flink on production, we do many works about the stability. Take the failover, for example. In Flink, if one task or the job manager fail, the whole job will be restarted. But in Blink, we change this. For the at least once mode, if one task fail, only the connected source will be rewound. And for the exactly once mode, if one task fails, only the connected components will be rewound. And even the job master fail, the yarn will relaunch it, and the job master will recover its state from HDFS and the zookeeper. And all the running tasks is not affected. So Blink failover has less cost and may recover fast. Okay. Besides to the runtime improvements, as mentioned before, Blink also provide a new job UI, which can show more runtime metrics for the job, such as the job resource usage, CPU and memory, and the task metrics, such as the TPS latency and the message transfer delay from upstream to downstream. Also the checkpoint and states detail metrics. And we also put the metrics into OpenTSDB and visualized by Grafana. Okay, finally, Xiaowei will show the challenges and future of Blink.
Thanks, Ben. So we did a lot of work on Flink to make sure it's suitable for production use at a very large scale. And we want to continue our work. First, we want to continue improving the optimizations we are doing in streaming. This includes more optimization in the failover to make it even faster and cheaper in the system. In addition to the reliability improvements, we also want to make sure the performance of Flink gets improved continuously to make sure it's the most performant streaming solutions out there that can provide the low latency, exactly one semantic, and exactly one semantics. In addition to the improvements we are making in the streaming part, we are also working on improving the batch mode in Flink to make sure its batch mode can go on large-scale production use as well. And we have already started porting our machine learning jobs into Flink, and it's already functional. We should be able to see it in production in a couple months. This job is one of our largest jobs, and it's going to run on over 1,000 machines. And as our traffic gets larger and data gets larger, we need more and more resource, which translates to larger and larger clusters. We want to scale Flink to even larger clusters to handle our future workload. In addition, finally, but the most importantly, we want to make sure we contribute whatever improvements we have made to Flink back to the community. We strongly believe in the collective effort of a community. That's how we get here. And by contributing our work back, we can help others, and we can also get benefit from the community. So we are going to meet with Costas and Stephen from Flink after this talk to discuss more details. I think that's it. We have about 6 minutes for questions. Yes?
Thank you. Great talk. This is Slim Bantaji from the Flink community. My question is related to the size of your cluster in production. If you can share a little bit, or even maybe configuration, hardware configuration.
Yeah. Yeah, so the question is the size of our cluster and the configuration. Our cluster has over 1,000 nodes, and it's a hybrid cluster, which means the same cluster will run MapReduce jobs as well as streaming jobs. It also has HBase running in the same cluster. Yes?
What type of machine learning do you want to run on streams?
That's a very good question. So what we are doing is online learning. Usually, in machine learning, we build model every day, and which is actually good enough in most use cases. But in Alibaba, if you are familiar with it, they do promotions from time to time there is one particular large promotion is on November 11th, which is called the single state sale. So on this day, a lot of products go 50% off. So the transaction volume is huge, and the user's behavior is so different from what they used to be. So whatever model you trained before that day is not going to do extremely well on that day. So there is a need to do machine learning at real time on that particular day. And we have seen very good result by doing that. Yes?
Do you have some feel for how much data you can push through Flink and how many transactions per second you can push through?
We have some preliminary experiment. The throughput is amazing. I think you can, on a single call, you can easily achieve over 10,000 transactions. You can process over 10,000 records a second. We haven't done much tuning yet. Yes?
Is it per code or 10,000 on that?
That's what we measured. We haven't really did much performance tuning, and we already get that result. That's more than enough for our purpose. So we haven't done much improvement on that.
So
Yeah.
I understand Alibaba team already using other technologies such as the Spark and the JSTONE. And how do you compare? What's the relationship between your project and those other efforts?
Yeah, that's a very good question. So Alibaba is a big company, and we evaluate and use different technologies. For example, in terms of streaming, Alibaba is also a big contributor in Stone. Alibaba invented the JSTONE and contributed back to the Apache community. We are actually working together with these guys to make Flink better. It's a joint effort now. Yes?
When a stream topology fades or a failure occurs, how much time does it typically take to restore the topology?
That's a very good question. The question is, when a failure happens, how much does it to recover from the failure? The answer is it depends. If the failed node does not have much state, it can fail over very fast, like in a few seconds or 10 seconds. But if it has a lot of state, like gigabytes of state, you need to download the state from HDFS, which may take minutes.
When you made Flink yarn aware, did you also leave the mode in where you can run it just on a standard computer as a Java process?
So you mean, do we still support the standalone mode?
Yes.
Yeah, that's for now that is broken, but we have had a very comprehensive discussion with Flink guys, and we are very close to a design that allow us to plug in different kind of resource managers, including standalone resource manager. When that happens, Flink will be able to support yarn, methods, and the standalone mode very well.
Do you have some timeline of when you're going to contribute that back to?
I will say yesterday, but that's my hope. It's really as soon as possible. I believe the earlier we contribute back, the community will get stronger, and all of us are going to benefit. Okay, thanks a lot for everyone. If you have more questions, feel free to talk to us.